Robot tour guides have been applied in different environments because they save human labor and can ease the discomfort during social interactions. While previous work covers diverse topics related to navigation and social interaction between human and robots, they mainly focus on a single robot tour guide. In practice, it is unlikely that only one robot will be used to guide all of the human visitors. This work presents a framework for multi-robot tour guiding in an uncertain environment. Suppose we are in a museum, a city's downtown, or other situations where there are multiple interesting places to visit. Some human visitors arrive and each selects several places of interest that they want to visit and asks for a tour guide. We hope to use robots to guide them through the tour. However, there are fewer robots than humans, and therefore we have to split humans into teams. As an example, we can split the humans into such 3 teams. And meanwhile, the robot should generate efficient routes according to human-requested places of interest. Overall, we want to simultaneously generate the optimal routes and schedules as well as the optimal matching between human and robots, such that, under limited resources and time, a minimal number of human requests are dropped. Formally, we want to optimize the weighted sum of the human's request and time cost subject to multiple practical constraints. In this work, we consider routing constraints, time window constraints, where some places of interest only opens at a certain time, team size constraints, human dependencies, for instance, some people might want to be in the same team, sequence dependency, where for instance, visiting one place requests you to visit another place first. Note that there is also uncertainty in the traveling and visiting time. We call this tour guide problem a simultaneous matching and routing problem because it contains a bipartite matching where humans should be matched with a robot and a vehicle routing problem where optimal routes should be found to minimize some objectives. Since the vehicle routing problem is NP-hard, this SMRP problem which contains the vehicle routing problem is also NP-hard. Therefore, this places a challenge to the optimization. Looking at the problem structure, if the routes are fixed, then we deal with a bipartite matching problem, and polynomial algorithms exist for such a problem. If we fix the matching, we deal with the vehicle routing problem. Moreover, since each robot only needs to consider the humans in its own team, the routing of different robots are decoupled and the problem reduces to a multiple single vehicle routing problems. Though a single vehicle routing problem is still NP-hard, there exist many algorithms that efficiently find very good suboptimal solutions. According to this analysis, one question that we want to ask is, could we leverage these previous solvers to solve the SMRP? According to our approach, we first initialize the matching and the routes randomly and iteratively improve the solution. In each iteration, we first fix the routes and solve a matching problem, and then fix the matching and solve multiple routing problems. Such an iterative approach is called a large neighborhood search algorithm. Comparing to a small neighborhood search like gradient descent, a large neighborhood search finds the next solution in a much larger neighborhood around the current solution and take a large step each time. Here we show the results of an example problem with 4 robots, 10 humans, and 10 places of interest for the humans to choose. In this example, each human can request up to 5 places to visit. The time limit for the tour is 500 seconds and the model considers the uncertainties in the travel and visiting time. In the results, we can see that human 2 and 8 are in the team of robot 0, human 1, 4, and 9 are in the team of robot 1, and so on. The routes generated are in the figure on the right. The largest problem tested in this work contains 50 robots, 250 humans, and 50 points of interest. And the problem is solved within 2 minutes. To test whether the model that considers time uncertainty generates more robust plans, We develop a simulation program using rules and evaluate whether the generated plans can ensure that the tour is completed within the time limit. For the simulation, we add a local navigation planner to each robot to generate actions and navigate according to the routes given by the multi-agent tour planner. The traveling time in the simulation is uncertain as there are incorrect navigation actions, and the time that the robots wait at a place of interest are sampled from Gaussian distributions to simulate the actual cases. A view of the simulation is shown here. There are 3 agents navigating between the places of interest in this example. Their camera views and routes are marked here. According to the simulation evaluation, our model keeps the time limit even with crude estimations of the actual uncertainty. In conclusion, this work presents a framework for multi-robot tour guide under time uncertainty. We did comprehensive computational evaluations of the scalability and the solution quality of the proposed algorithms. The robustness of the solutions are demonstrated through photorealistic simulation case studies. For more results, please refer to our paper.